Designing our DIY 3D printed drone chassis, this time on Hack 5. Hey everyone, Glytch here and welcome back to Hack 5. Today we're going to be working on our DIY 3D printed drone chassis. Specifically, we're going to be taking a look at designing it in Fusion 360. A couple videos ago, we actually went over what software you might want to use and why. While Fusion 360 isn't open source, it is the most flexible and it is free for personal use. Make sure you read that asterisk there. We're also going to be looking at the various types of drone chassis. We're going to talk about the material requirements, and we're going to actually just design it, CAD it up, take measurements of our parts, and make a frame. The tools and software you're going to need are Fusion 360. If you're using that, you could also follow this roughly in some other design software like Onshape, or it'd be interesting to try SketchUp. Other than that, you're going to want some digital calipers and your motors and flight controller, cameras, and so on. And make sure you go back and watch the previous videos in this series if you're actually going to follow this along. They're basically required watching to some extent, because to design a frame, you need to know what parts you're designing the frame around and why those parts are important, and so on and so forth. And that's basically it. So let's dig right in and start designing. So here we are in Fusion 360. First things first, we need to decide on what type of frame we want. There's a graphic on screen now from a site called Drone Nodes, and it shows square, true X, H, and all these other different drone shapes. It doesn't show the couple I'm actually interested in designing today, and that is something of a modified H. Actually, it's probably closer to an IX frame. Now, this design can be seen somewhat in the GEP-RC Baby Croc that Darren and I did a shootout video on some time ago. You can see that here. If you look closely, it's almost straight across up top and has an X type of shape on the bottom. This allows us to mount our crossfire antennas straight across up front, and it also affects handling in some relatively good ways. The flight controller takes up a lot of the weirdness of various frame designs, so if you're wanting to try something strange, feel free, because odds are the flight controller will make it flyable. The frame shape you choose really just comes down to what type of handling you want, and mostly personal preference. I personally really like this layout because it gives you a nice large center section to install all your parts to, with lots of room to work, and then the battery can go on top. So with the frame type chosen, we now need to figure out the distance between motors so that the props don't overlap or otherwise cause turbulence with each other. And we also need to figure out how big we want our center section to be, where all of our payload and everything's going to go. This is going to be a relatively basic FPV drone, so we don't need a huge area. The GEP-RC has a really long avionics section because it has a DJI Vista in there, as well as the flight controller, a GPS module, a high-definition camera, and all kinds of other relatively large components that we aren't dealing with. So obviously this drone's going to be a lot smaller. One weird thing to keep in mind is the Zeus flight controller we're using is kind of meant for a 45-degree mount, which means it will be diamond shaped. If the drone's going this way, then the flight controller is going to basically be mounted like this rather than like this. You can offset this in the flight control software, which we'll get into in a couple videos from now. However, for simplicity's and reliability's sake, I'm going to mount it this way. I just wanted to make that note here because this flight controller probably wasn't ideal for this, but it's easy to get. So the easiest way to figure out how big our frame should be is to take our propellers, and you can either just use the measurements provided, or you can take your calipers and get an idea. In this case, these are going to be 70mm propellers. So we're going to go into our CAD program, select top here, and we're going to make a 70mm circle. And we're going to repeat that a few times for all of our props. Now we have basically the disc area of our props, and we can move those around and get a rough idea of how big our drone should be, what shape it should be, and so on. Now the rule of thumb is you want roughly 1.5 prop diameters between the various center points of the motors. In this case, we have 100mm there and 100mm there. That also makes it square, which means our tuning for roll and pitch will be basically the same. Weight distribution can affect that somewhat, but with a square prop layout, we don't have more pitch authority than we do roll authority or vice versa. It will be equal pitch and roll authority, which for beginners is a really good thing because the drone handles exactly as you'd predict it to without any extra tuning. Now, it's possible to build a longer drone that handles, you can turn down the pitch strength and so on, but that gets into a little more advanced stuff than we're looking to get into with this design. Next step is to throw down our center chassis block. This is basically going to be where we mount everything. In our case, we want it to be at least 43 millimeters wide, so we'll call it 44 millimeters wide, because that is how wide the screw holes on our flight controller are. Now, one trick we can actually do here to make our life a lot easier is to only design half of the drone. This saves a lot of issues with symmetry. Basically, we know we want this to be 40 millimeters wide, so I can actually, or 42 millimeters wide, so I can just make this 21 millimeters wide, and then once I have the whole left side of the drone designed, I can go through and just clone the whole thing, arms and all, and copy, basically mirror it and make the other half. That way I'm doing half as much work for a full drone. Now, it is acceptable to have the props overlapping the center chassis somewhat. This will affect your thrust output as well as cause more turbulence on the props. So for a high performance, perfectly tuned race drone, this isn't ideal. For a backyard flyer like we're designing today, it's fine. Now, you could always extend the arms another few millimeters up and out, and that would completely clear this, but it also makes the drone a bit bigger, a bit heavier, and so there are trade-offs there. Now, the next thing we want to do is make the rough layout of our arm. Now, we know the motors have a 14 millimeter mounting foot, so I'm going to make the arms roughly 16 millimeters. Now, the great thing about the drone we're designing today is we don't have to be super worried about snapping arms from pure thrust. This drone's light enough that it could probably handle a couple of crashes too without snapping arms. However, drones I've designed in the past would actually break their arms purely from thrust because they generated A, so much thrust, and B, the center sections were so heavy that the motor basically levered the arm over and caused it to snap midair. Part of that was I was using PLA back then, and we're going to be using PETG plastic today, which is stiffer, a little more flexible, and is still easy to print. ABS I found to be one of the ideal filaments for designing drones because it was fairly flexible, which sounds like a bad thing. However, for crashes and absorbing impulses like full throttle bursts, it handled a lot better and you could get away with a much thinner frame. Today, this frame's going to have to be thick enough that our screws don't go through our motor windings, which I'll touch on in a little bit. And that alone is going to provide enough strength at the voltages and thrust and everything we're running that it will make it a non-issue. We're not super worried about how thick the frame needs to be. Next thing, we're going to design our diagonal arms in the rear. This one gets a little trickier. To make my life easier, I'm going to go through here, double check this. Oh, I need to fix that. Now I'm going to use a trick here to design these diagonal arms. First, I'm going to check my measurements up here. That's a 14 millimeter circle. I'm going to go down here and make another 14 millimeter circle. But I'm also going to put a 14 millimeter circle. And all of this is relatively arbitrary. I'm not basing these measurements on anything other than gut feeling and the size of the various hardware I'm using. And I can get away with that because, like I said, this is a relatively forgiving drone design, and I'm designing it on what I think I want it to look like. Modern flight controllers are so adaptable that you really don't have to put a load of thought into the design of the frame because the flight controller makes up for so much of it. So we're going to go ahead and extrude the base part of our frame and adjust it a bit more as we go. We actually don't need those parts because those are going to get mirrored. Now, real quick before I actually run this extrusion, like I was saying earlier, one thing to be wary of is when you're screwing the screw into the motor. I'm not really sure how well you can see that, but it's possible for the screw to go through the footing and continue into the motor windings, causing them damage and to short them out. So we want to make sure our frame is thick enough that we don't need to use washers or anything, because we'd rather have a thicker frame than be using backing washers to make up that space. So in our case, we need the frame to be at least 3 millimeters thick. Anything more than that, actually, and we'll need to use longer screws and so on and so forth. But I want to use the screws included with the motors because I don't want you to order new screws. So we're going to go with a 2.9 millimeter. Once we actually get our component layout figured out, we can hollow out a bunch of this, basically how the GEP-RC did, and that's carbon fiber. We can go through and make speed holes and all that, and that will considerably lighten our frame design. One other neat thing about 3D printing, and we'll touch on this more in the next video when we actually print our frame, with 3D printing, we can make parts that aren't solid. So this actually has an advantage over traditional drone design. Like that carbon fiber I just showed you, we wouldn't necessarily need to make our speed holes all the way through the drone. We can use less infill or thicker walls and so on to save weight and adjust our strength where we want it. Now the next step is to design our motor holes. Now we could sit here and measure the footing of the motor here and go through all that, or we could just look up the part diagram. So in our case, it is a Zing 1404 4600 kV motor. Most drone parts come with a layout like this. We can go here and we know our bolt pattern looks like 9 millimeters in diameter and it uses 4 M2 screws. So we will do 9. We know it uses 4 screws in a perfect X configuration. Now, one thing about 3D printing is it never recreates holes perfectly because the material over extrudes a bit. So I'll oversize the holes by usually 25% or something like that, depending on the size of the screw. So these 2 millimeter screws are going to be getting 2.5 millimeter holes, and odds are they'll still need to be drilled out somewhat. And you can see I did that in a relatively 45-degree angle, so the cable will actually run up the arm. And then up here, we'll do that same thing, but I'm going to give myself some guides. So that's 135, and we know it needs to be 9 millimeters, so we'll go 4.5. We'll go up here, and we'll do that as a 9. And then, again, we'll go this way. Now, one thing I forgot to add here that we need to do real quick is pretty much every motor has a center hub with a lock washer on it. And that lock washer needs to have a relief hole cut in the frame, or else if it will get squished and basically seize up the motor, and you can burn out motors exceptionally quickly. So in our case, we need to measure this. And it looks like the bearing is about 5 millimeters in diameter. As I said, we're going to make that about 6 because 3D printed holes are pretty much never, we'll go 5.5. 3D printed holes are pretty much never the size you design them at. Now you can see there is actually a little concern here on how little material is between this. And so I think I'm going to actually go ahead and take my chances and bring that in about 1 millimeter in diameter. I would rather have a little more material there, and I can always drill it out later. That's one thing about 3D printing. It's, as with most methods, it's easier to take away material so that you don't need to reprint an entire frame. So this change, if it is actually too tight for that center washer I was talking about, we can go back later with a drill bit and drill it out instead of having to 3D print a whole new frame because we made it too big and then ended up snapping an arm or whichever. One thing to mention is you can use this pattern tool. Probably not rectangular pattern. Where is it? Yeah, you can use the circular pattern tool to do what I just did here. But I find for these 4 motor holes, it's easier to just do it by hand instead of using the pattern tool. If it was more than 4 holes, I'd probably use the pattern tool. It just takes a little bit of setup. Now, real quick, we're going to mirror this, as I was saying before. We want to mirror the body across this plane. We want it to join it. You hit OK, and boom, drone. Now, that is a very wide center section. Let me check my measurements on this. Yep, 42 millimeter. Okay. You can kind of start to see what our drone's going to look like here. Now, we want the bottom of the drone to be as flat as possible so that we don't have to use support material or anything when we're printing. And so we're going to leave the bottom untouched. So any kind of stiffening or cable guides or anything we think we want to do across the top of the drone. Now, I'm going to make this drone very simple. A lot of drones have a top deck that adds extra stiffness and so on, and that's something we could add later. However, I want to make this just basically a flat plate. I want to print one piece and have our drone frame. I don't want multiple parts that need to be assembled and so on. And so to get that rigidity and stiffness I need, I'm going to actually go through and right along the edge here, I'm going to put some pieces like this. I'm just kind of eyeballing these. And this will give us rigidity in the long axis here. We'll bring those up about 3 millimeters as well. And then I'm going to give us some cable guides. Now again, one trick we can use so that we don't have to do this work twice, instead of just extruding it through here, we can actually extrude it all the way through the other side. And that gives us our perfectly matched cable run. Now while we're up here, I'm going to fillet of fish, the front of these. Now obviously the rear doesn't need those same cable guides because these stiffening arms don't extend that far. I do think I want to extend these a little further though. And again, we will just fillet that. Now, something we can play with as we actually flight test this drone is dog bone, like bringing in the arms right around here to reduce material and also reduce the surface area of the arm so that less thrust is getting redirected and less turbulence being generated. And basically the thinner the arm, the more thrust goes past it rather than kind of swirling around there. However, I don't want to mess with that right now because I'd rather have too thick of an arm than too thin of an arm that will break. And that's the great thing about 3D printed drones is we can revise our design and improve it as we go. When we break something, we make that a little stronger. When we think we want to reduce some material and make it lighter, we can do that as well. And again, odds are, if I really wanted to, I could take out probably a good 3 mil on either side of this and just run a single stiffening joint down the middle. And I'd have a stronger arm than just this flat piece of plastic. Next up, we're going to take some measurements for the flight controller. It looks like it uses a hole pattern of about 35 by 35. And we want our flight controller to be as centered as possible. Again, modern flight controller software has gotten really good, so you could bias it towards the front or towards the rear and adjust for it in software. But I'm trying to minimize how much tuning we need to do. So we're going to put it roughly center. So right about here. And that's the center of the props rather than necessarily the center of the frame. So I said the holes are 35 millimeter. So off center, we're going to go. Now it is unfortunate that I chose a flight controller that is an X shape. It does make this a little silly. It is not an ideal use of space, and the center of this drone could be much narrower if you used a flight controller like this. Like I said, you could also adjust it in software, but I'm trying to avoid that. And again, we will make a 2.5 millimeter hole in all 4 of these. Now, another quirk of this flight controller is it has a USB port sticking vertically out of it rather than an edge. And so we need to account for that and make a hole for it to go through the bottom. I don't want it sticking up through the top because it's possible it'll get sheared off. If it's aiming down, it will get less obstructed. Also, all of our motor solder pads are on the top, and I want those to be easily accessible. And again, I don't want to have to change the orientation of the flight controller in software any. So I'm going to give a fairly large relief here. If it's not clear, I've taken no professional courses on designing in Fusion 360. It's something I kind of taught myself, and I'm sure a lot of what I'm doing here is not ideal or not correct. But this isn't a Fusion 360 tutorial, this is a drone design tutorial, which I'm going to say makes it okay. And again, we're going to add some nice little round bits here just because I don't like sharp corners. Alrighty, I think that's all we need to do for the flight controller, which also covers our VTX because the VTX mounts across the flight controller, which makes this, I really like this setup. It's one less thing I have to account for. We do need a place for our receiver. A lot of drones will just throw the receiver wherever with some double-sided tape, and that's absolutely an option here. And then that leaves our camera as well. Oh, and we also need to cut some slots for the battery strap. Like I said, we're not going to design a top deck for this at the moment. So we're going to be putting the battery on this drone on the bottom. And so the easiest way to do that is to just go in here, and we'll add the Velcro strap later, and that will just hold our battery on the bottom right here. Next up is the camera mount. Our camera is right at 14 millimeters wide, so we'll probably do a 16 millimeter gap, and we can use spacers. And it's 15 millimeters tall, so we'll need the camera mount to come up at least 8 millimeters. And we do want it to be protected by the front of the frame somewhat, so we'll bring it back. Going to use the center line here to make it symmetrical. So we'll bring this out 2 millimeters. Now the one unfortunate thing here is we're going to be working against the layer lines of the 3D print. And so this camera mount probably is not going to be the strongest thing in the world. We can make up for that a little bit with thickness and some fillet joints. So we will do that. We only need it to be about 10 tall, because the mounting holes are going to go at 8 millimeters. I want this to come down a little further because I have to account for half of the mounting screw hole. And as we did before, we're going to punch that through both of them so we don't have to repeat our work. Next, we're going to pull some fillets here to increase the rigidity of this mount a little bit. It's probably excessive, but do this just to clean up those sharp corners. And we're also going to do this out here. I think that's it. We just designed a drone chassis, more or less. Now you can go through and clean some other things up. Like if we wanted to make it look a little more pro, we could go through and fillet all of these joints. I do think I'm going to fillet these top ones, just because. And I'll probably also bring this. Anywhere you have sharp corners, there's going to be stress concentrations. So just keep that in mind. Fillets, while they look good, they also serve a practical purpose, and that they are relieving some stress. Especially in any time there's a lateral movement. So if this arm caught on something like a crash or something like that, these fillet joints will take up a lot of stress rather than giving you stress marks. As someone who's crashed a lot of 3D printed drones, I've gotten pretty good at determining where the weak points would be. And there we go. I think I will cut a couple of zip tie holes for our crossfire. I want to use a hard mount crossfire, or a rigid crossfire antenna like the GEP RC uses, rather than the lighter antennas, because I find that I chew up the lighter wire antennas way too often. So anytime I can make room for a rigid antenna, I want to use one. Like I said, the battery is just going to be mounted with a strap across the bottom, and you can tell the bottom of our drone's completely flat, so it will fit on our printer. Now, one thing I didn't check, let's take a look at just how big this frame is. Look at that. It's 120 by 116, 117. So this will fit on the Monoprice Mini Select. Now I have bigger printers I'll be using, but I want to make this as accessible as possible, and the Monoprice Mini Select is a 120 by 120 millimeter build area, and that's common on a lot of budget and lower end printers. So this drone chassis will fit on the cheapest, simplest of printers. I'm pretty stoked about that, considering I didn't necessarily make that a design requirement. And there we have it. We're ready to go through and print this and assemble this. In the next video, we're going to, like I said, print this out and start assembling all the hardware. And the video after that, we're going to go through some of the electrical documentation, talking about how to solder everything together, where everything goes, best practices. And then the video after that, we'll look at the beta flight software we're going to be running on this drone and actually take it for a test flight. Now I got to figure out how to edit this. Editing a video on CADing software and keeping it interesting is going to be interesting. So I'll get back to you on that. Thank you all for watching. I've been Glytch. This has been Hack 5. Glytch out.
Thanks for supporting Hack 5. Find all our shows, community, and pentest products at hack5.org.
Hey everyone, Glytch here, and welcome back to Hack 5. This is Hack 5. Hack 5.